Okay. I think we're ready to rock and roll, or are we still waiting for anybody?
I think we're good.
This is it. We're going. Awesome. Well, hello, everyone. Welcome to our second webinar of 2023, MABA's webinar. This series is titled Innovative Solutions for Smaller Utilities. My name is Logan Jury. I'm a MABA member and fellow biosolids enthusiast, and I'm happy to be asked to be a moderator here today. So the plan for this is we have 3 presentations for the webinar. Each presentation is going to be approximately 15 to 20 minutes. And then we're going to reserve some time at the end of all of the presentations to do a Q&A session. So once we get through all 3 presenters, we'll do some Q&A. So during the presentations, as you're intrigued or have some questions, please use the Zoom Q&A feature at the bottom of the screen to submit your questions. Once everything's wrapped up, I'll work through the questions. I'll pose them to the various presenters and get them addressed. So with that said, we can kick things off with our first presenter, who's Valentino Villa. He's the COO of Bioforce Tech. His presentation is titled Truly Sustainable Biosolids Management, the Bioforce Tech System. And just a brief background on Valentino. He's the co-founder and COO at Bioforce Tech Corporation. He earned an Italian professional designation for an industrial expert in the field of engineering that is recognized as an industrial engineer outside of Italy. So since co-founding Bioforce Tech in 2012, Valentino and his team have been rethinking every step of biosolids management to prepare for a carbon-free future. And Valentino believes that Bioforce Tech's biochar R-carbon process is a resource, which is why his team are investing in research development to expand the applications for biochar beyond soil amendment. So Valentino lives in California with his wife and 2 kids. So welcome, Valentino, and I'll turn it over to you.
Thank you. Thank you so much, Logan, and thank you so much, Mary, for having me today. Hello, everybody. All right, let's see if things work first. Everybody can see my screen?
We got you.
Awesome. Just FYI for everybody listening today, my connection has been a little bit spotty this morning. I just wanted to make that note. We've been hit by a pretty severe wind and rain here in California. So just FYI, in case I freeze or connection is getting spotty, please let me know and I can repeat myself, of course. All right, so I always begin with a quick introduction of the company. So we are Bioforce Tech Corporation. We are based in South San Francisco, here in California, in the Silicon Valley area, and we incorporated the US business in 2012, as Logan anticipated. Our mission is to protect nature and human health by providing technologies that deliver a zero waste future. So our goal is to transform organic waste and biosolids specifically into sustainable products. So if we look at nowadays situation in the United States, mainly about 90% of the biosolids and residuals are utilized between landfill and land application. These 2 options that have been going on for about 30 years are now experiencing some pretty severe challenges. Of course, landfill is probably the most impacted as far as we are experiencing a tremendous loss of value, potential contamination with PFAS, PFOA, CECs, leachate, and of course, greenhouse gas emissions. And a bunch of states already have in place a landfill diversion for organic waste. And of course, costs are rising and capacity is becoming less and less available. Land application on the opposite, we of course support land application for those biosolids products so long as we can understand if they're actually being cleaned up, if contamination is really not present. But the point compared to, again, the previous 10, 20, 30 years. And many counties and states are posing bans on using biosolids products on the land app. And we have the same Problem at the end that is raising costs, limited capacity, if not our capacity, again, in some states or jurisdictions. So at Bioforsa Corporation, we do see waste as an opportunity, especially nowadays, with mainly 4 objectives and goals, right? So we can generate renewable energy from those biosolids and residuals. We can remove contaminants, sequester carbon, and creating renewable products from those biosolids. We started developing full-scale systems, and the first installation in the United States market is back in 2017 here in the San Francisco Bay Area. And since then, we were able to increase our reference and installation list between Italy and North America. And those are the main 2 markets that we serve at Bioforsa Corporation. So looking at the North American situation, the United States of America, we now have more than 7 biosolids installations with more than 20 bio dryers and 6 pyrolysis systems procured. Some are in operation, some are in construction. A couple of weeks back, just a pretty fresh announcement, we just received a new order from the city of Brentwood here in California for 8 dryers and 2 pyrolysis systems. It's about 7 MGD treatment facilities. So great news for us. And again, we're scaling and installing more and more systems across the US and Italy. Looking at the Italian situation in the picture there, we have installation from north to south, more than 8 biosolids installations with more than 18 bio dryers and 2 pyrolysis systems. Same concept, some are in construction, some are operational. And again, the Italian market is another very good market for us since the very dramatic situation with biosolids and residuals there as well, where they're seeing increasing tipping fees and costs of disposal, and options are very limited as far as what to do with those biosolids. So the Bioforsa system is a 2-step process. So we have a first step of bio drying. So it's a non-conventional drying system that instead of relying on fossil fuel or expensive energy sources, it mainly utilizes bacteria, so biology, to be able to dry biosolids very quickly, very efficiently, and very reliably in order to get to a dry Class A product with a fraction of the energy that any other dryer will otherwise need. So once we're able to get to a dryer product between 80 to 90% dry solids, the second machine comes to play. And the second machine, the second part of the process is our advanced pyrolysis system that has the main goal of transforming those dry biosolids into high quality carbon or otherwise named biochar. We call it our carbon as our trademark and sort of distinguishes factor as far as the quality and the type of product that we can produce throughout our system. So again, our goal is very much to stop producing the waste, to remove CECs such as PFAS, PFOA, microplastics, and so on through the second step of pyrolysis, be able to produce energy that can be utilized by both processes to deliver an energy neutral process from a thermal standpoint, and ultimately be able to utilize our carbon to make sustainable and beneficial use products. Today's webinar is mainly focused on smaller utilities, which our systems very much comes to play and very much is able to serve the small to medium scale utility, with the sweet spot of the combined train, so biodrying and pyrolysis, between 1,000 wet tons per year or less, up to 10,000 wet tons per year. So pretty much to give you a reference in million gallons a day, between 1 to 7, 8 million gallons a day, average daily flow. That is truly the sweet spot of how to best implement our technology within the wastewater treatment plant. So the first step, again, is called the Bioforsa bio-drying system. Is a biological batch drying system that operates at a maximum temperature of 160 degrees Fahrenheit, so roughly 65 to 68 degrees Celsius. Utilizes a combination of biology, so utilizes bacteria that are already within the feedstock itself, within those biosolids, in order to raise the temperature of the biomass naturally without utilizing any energy from the outside. Most of the drying part and batch is done and covered by the biological parts of bacteria, and the remaining portion of the bio drying is going to be done through a recirculation of energy from the pyrolysis step, if of course we have pyrolysis combined with the drying system, or from a regular source of hot water at about 200 degrees Fahrenheit. So the resulting objective here again is to be able to remove water as efficiently and as reliably that it can be done, with the goal of producing a Class A compliant solids by EPA 503, with about 70% less energy that any other dryer again will be able to replicate to the marketplace. It's a fully automated system, of course, that runs on a 24/7 basis, up to 95% of running time, so up to 8,500 hours per year with very low and simple maintenance. Some key highlights here, the average capacity of a single biodryer. So again, it's a modular and scalable system. The minimum scale is going to be a single unit, and then we can expand with multiple units. And the average capacity of each module is about 1,000 wet tons per year, assuming 20% solids going in and 90% solids as the product that is discharged. We have an average electrical consumption of about 25 to 35 kilowatt hour per input ton, and the thermal consumption without pyrolysis is between 0.9 to 1.2 million BTU per input ton. Minimum requirement for solids concentration after dewatering is 17%, and the system can process stabilized or unstabilized solids, so digested and or undigested solids, so long as we have a minimum of 17% dryness, so after dewatering, and a minimum volatile content of 45% on dry basis. The output from the biodryer can be very much adjusted between 70 to 95% dry solids, depending on how long we keep those biosolids inside the batch, inside the vessel. And again, it will be Class A compliant by EPA 503. It's a modular and scalable design where all of our units are going to be skid mounted and pre-assembled and pre-built at the factory. So very easy for us to scale at any time and increasing processing capacity just by adding units as we want to grow. And of course, the unit is already Class 2 DIP2 ready following the NFPA 820. This is how the biodryer is delivered and built. Is comprised of two skids. The skid to the left having the main cylinder with the catwalk and the screw conveyor for feeding purposes with motors and sensors. And we have the air skid to the right that has the blowers, the heat exchangers, and all of the piping that will pretty much make a complete system that anybody can install directly on site. Dimensions, each biodryer, of course, has been maximized to be able to be pre-assembled and pre-built and delivered as a fully built piece of equipment. So we have a length that is 40 feet and it's 15 feet wide and about 14.5 feet tall. Some pictures to also make you understand better scale and how we can expand. We go from installation that have a single dryer up to 3, 4, 6, 7, and so on. So you can see some slides and some installations here going from 3 bio dryers, so about 3,000 wet tons capacity, and this is one with 7 units, so about 7,000 wet tons a year capacity. 4 units, about 4,000 wet tons, and so on. You can understand again the modularity, the disposition of these units once they are delivered to the client's location. Again, we can expand at any time just by leaving enough space and work with the configuration to best accommodate units for the future in case that will be one of the goals. We do manufacture our units nearby Monza, nearby Milano, in the northern side of Italy. We have a great manufacturing facility that has about 45,000 square feet of space available. We have about the capacity of about 30 machines per year that we can manufacture and fulfill orders for customers in Europe and, of course, in North America. So switching to the second step, again, is our advanced pyrolysis system. So after we were able to dry those biosolids very efficiently there on second machine, the advanced pyrolysis system has mainly 3 goals. The first goal is, again, to produce the highest quality carbon in form of biochar, our carbon, that's how we call it, without the production of any tars, oil, and hydrocarbons. So very clean for the process, but also for the end product that will be having no contamination and no resulting bio oil being condensating on the char. The second objective is to be able to create renewable energy that the system, the pyrolysis system, will be utilizing itself to self-sustain the process on a thermal standpoint, and it will be able to feed the biodryers back with some extra energy to deliver an energy neutral process from a thermal standpoint. The unit follows the same concept here, so modularity and scalability. And the third objective that nowadays is actually pretty important, as it actually an indirect effect of doing pyrolysis the way that we do, is to be able to remove CECs such as PFAS, PFOA, microplastics, and so on. Permitting wise, we started our journey with the EPA in 2015, receiving the approval as a non-incineration technology formally by the EPA. And we received the permits to operate in the most difficult and stringent air district in North America. There is the one here in San Francisco, as well as in other jurisdictions between Pennsylvania, others in California, Washington State, Oregon, and so on. So very permittable. We went through already all of the difficulties of permitting the first unit and facility here in San Francisco. Now, new permitting applications are much smoother and quicker, of course, due to all the data and source testing that we collected across the years. So a quick look at a mass balance here, begin with an assumption of 1,000 wet tons per year of solids at 20% solids matter. After the bio-drying, those will be reduced to approximately 250 tons of Class A, between 80 and 90% dry solids, and further down to just 75 tons remaining of our carbon biochar, starting from the 1,000 wet tons. So we achieve a 90+% reduction in mass, that of course will equal to 90+% reduction in trucks and logistic to be dealt with compared to the wet biosolids at the beginning. Made with our carbon, again, the name and the trademark of our biochar that we can produce through our system is called Our Carbon. The concept is very easy and straightforward, right? So we divert biosolids, we divert organic waste from disposal in the landfill and or land application. We transform those biosolids and we apply our carbon where it's needed the most. What we've been doing across the past 6 to 8 years of us, producing, developing markets that were not existing for our carbon and for biosolids derived biochar, mainly range between the soil amendment used for those biosolids derived products to pigmentation and concrete additive. We've done a great work. Of course, we have some IPs, patents, and trade secrets, how we best apply this product. We have offtake agreements in place between Europe and North America. So the point here is that if a partner, if a utility decides to work with Bio4Sec and install our pyrolysis system on site to process their biosolids, part of our offering will also be to manage the entire production of our carbon at no cost to the utility for the next 20 years, while sharing some of the profits back with them. So here's a complete, switch in mindset, going from paying to dispose of a waste of biosolids, going to not having to pay any single dime to get rid of anything for the next 20 years, which is a game changer here, right? So you're not going to be dependent on anybody else for off-taking. Limited capacity, whatever options you have, but you'll be able to process and transform your solids in-house and having a consistent and guaranteed offtake for 20 years at no cost. I'm going very quickly here. I want to leave enough space for a Q&A at the end. Related to producing our carbon, we said it before that one of our goals is really to also prevent and sequester carbon. Through biochar production, we are fixing carbon in a fixed form, in a fixed way inside the end product. And LCAs that we develop with third parties that develop the beam model as well are showing that each ton of our carbon produced is able to prevent up to 10 tons of CO2 equivalent, especially compared to landfill disposal. So great benefits on a carbon sequestration standpoint as well, where the Bio4Sec system has shown to be the most effective in preventing and sequestering carbon compared to any of the other most common ways of processing, disposing of, or beneficially reutilizing those biosolids. Last topic I want to cover for today, of course, PFAS and CECs. We took it pretty seriously starting in 2018. Honestly, we didn't know back, 2016, 17, and so on, that pyrolysis was also going to be effective at removing CECs. There was not, this rush on, what to do with CECs back then. But starting in 2019, we started to, entertaining testing, and in 2020, directly with US EPA, at one of our full-scale systems here in North America. So with EPA, we identified 41 PFAS to be analyzed. The equipment used, of course, and tested was the biodryers and pyrolysis system. We ran a total of 6 one-hour tests, and we analyzed the wet solids, the dried solids, biochar, tap water, scrubber water, and stack sampling utilizing a novel method through FTIR and canisters. This is the picture of the testing site. We have, again, 3 biodryers and 1 single pyrolysis unit, average capacity of 3,000 wet tons input material. And results came back with about 20 compounds detected in the wet and dried biosolids, right? With different levels of, concentrations and level, but definitely good enough for testing purposes to understand the fate of those constituents. Results for biochar came back with non-detected, all across the 41 analyzed compounds, which was an amazing result that confirmed our first testing in 2019. But this time we also expanded more testing on the top and the scrubber water, and of course stack air emissions. So on the water situation, unfortunately, city tap water had PFAS and PFOA in there, not surprisingly. So the point is the discharge water from the scrubbing unit of the pyrolysis system had the same level of concentration and constituents as the city tap water that was analyzed going inside the scrubber. The million-dollar question was on the stack and the sampling for the air emissions. That again, we utilized a novel method by the EPA since they did not have an approved testing method back in 2020. Now they finally have it. So preliminary testing showed that really nothing was detected above the detection limit of the instrument through the canisters. 17 analyzed fluorinated compounds were not found. The FTIR detected some gases that may have been related to the gas that we utilize for the testing purpose. The point here is nothing was really detected, although we cannot make the claim that those were accurate and scientifically based because the testing method was not official, again, from the EPA, but it's already a very good start as far as understanding solids, water, and stack, what happened there. And this year, we're seeking new and expanded testing with many stakeholders and national consulting firms to finally understand, the fate of PFAS, having done inclusion and comprehensive mass balance for those compounds as well. We already received some preliminary testing, very encouraging, understanding and demonstrating these findings that really nothing ends up even at the stack. But we will be presenting with all the data and finding in the next few months as soon as we are finished with the new testing, again, set for this year. There's a great peer-reviewed article in case you want to read and learn more specific to the 2020 EPA testing that has been peer-reviewed and released in February 2022. So let me know if you are interested to receive a copy. I'm more than happy to share the link with you all. That was the end of it. These are my contact information in case you want to reach out directly. Again, we're based in San Francisco, California, and I think and I hope I was right within the time that I've been given. So thank you so much again, and I'll be here to answer questions at the end of the webinar. Thank you.
Thank you, Valentino. That was a good talk, and I think that's an interesting technology.
Thank you.
I probably have a question or two for you, but I've got to hold them too. So
absolutely, I'll be here. Thank you, Logan, again.
Of course. We're going to move on to our second presentation of the afternoon. This is going to be from Wade Yankee, who is a wastewater and residual scientist at Material Matters. Wade is presenting on operations changes at Silver Springs Township to meet Class B without capital investments. A little background on Wade. He has a wide array of water and wastewater treatment and consulting experience over a 12-year period. Relative to wastewater plant operations and troubleshooting, laboratory methods, practices, and solids processing and dewatering. Wade also has considerable experience in the development of biosolids beneficial use programs, permitting, and solids master planning. Wade has a BS in environmental protection from West Virginia University and a master's in environmental pollution control from Penn State University. And he is a certified wastewater plant operator. So Wade, thanks for being here. I'm going to turn this one over to you, and I look forward to hearing what you have to share.
All right, thanks, Logan. Thanks everybody for attending over your lunch break, and happy Pi Day to those who celebrate it. As Logan mentioned, the talk I'm giving today is operations changes at Silver Spring Township. Meet Class B without capital investment. I know this is an innovative solutions for small utilities talk, but I think it's important to think about those solutions not always coming from a technology perspective when we might be able to solve the problems with things that we have. Quick agenda. We'll take a quick look at the plant and sort of what spurred this little study at SSTA. And then I want to kind of review the path to Class B for the technologies that Silver Spring Township employs, and then take a look at some of their unit process, specifically their digester, some of the changes we made, and of course the results of those changes. Silver Spring Township wastewater treatment plant is located in Mechanicsburg or near Mechanicsburg, Pennsylvania. Of course, a small plant, about 0.8 MGD average annual daily flow. It's an SBR plant with biological nitrogen removal. They use a chemical for phosphorus removal. They do have aerobic digestion, and they produce about 1,600 wet tons of biosolids annually, being a little less than 200 dry tons of biosolids annually. So the challenge is Silver Spring Township has never had a beneficial use program in the past. They've always used a landfill, which is pretty typical for these kinds of small plants. And I think it was never a major concern for them, as they did have a competitive landfill price. Their last contract was at $70 per wet ton, including transportation. So likely a tipping fee of, less than $60 per wet ton, which if you do biosolids business in the mid-Atlantic, I think you'd be happy if you were getting that price. Unfortunately, that contract ends very shortly, and they're expecting increase of roughly 100% for their next contract, up somewhere in the sort of $100 to $120 to $150 per wet ton. So if that holds true, 100% price increase, that's about $112,000 annual increase in solids management costs. So at that point, they thought maybe they should take a look at some other potential solutions for managing their biosolids. Silver Spring contacted us to do a feasibility study to see if and how they can meet Class B standards without making massive changes to the treatment plant. They were open to some technologies. I think mostly lime stabilization, because they could input lime stabilization at the end of the process without affecting the treatment process that were already established at the plant. But our question was, can they meet the standards without adding any additional equipment? We know that they have aerobic digestion. We have a lot of clients that meet Class B standards with their aerobic digesters without lime stabilization. So we wanted to collect some data, review it against the Class B standards, and see if they already meet Class B and just don't know that they do, because they're not operating to try to meet Class B. So just as a review, we need to meet 3 sets of criteria to meet Class B. You need to meet the Table 1 pollutant limits, that's for heavy metals, Class B pathogen reduction, and of course vector attraction reduction. So these are the samples we collected, and our initial results, we found that, not surprisingly, this is a small plant with very few industrial connections. So we didn't see any problems in their metals concentrations. In fact, all of them were not only below the table 1 ceiling concentrations, but also the table 3 concentrations, which, we use for class A EQ standards. So, this is sort of what we would expect, and no changes are required to meet any of these limits. So moving along to pathogen reduction, if you have an aerobic digestion plant, you basically have 2 options to meet pathogen reduction standards for class B. Regardless of treatment technologies, we can all use alternative 1, fecal coliform analysis to meet class B standards. And then there is a PSRP, that's process for significantly reducing pathogens for aerobic digestion specifically. And that is, you need to maintain an MCRT between 40 days at 20C and 60 days at 15C. It is very unusual, we've found, to find plants that have enough digestion capacity to meet this. And also, of course, in this part of the country, there are significant parts of the year where we operate below 15 degrees C. But of course, we wanted to take a look at both of these options and see if they could meet pathogen reduction without making changes at the treatment plant. So we did collect samples for fecal coliform and had those analyzed, calculated the geometric mean. The geometric mean needs to be below 2 million for class B standards. That's dry weight basis. Silver Spring Township was able to meet fecal coliform without making any changes, which was encouraging. Of course, many treatment plants would prefer to use a process-based pathogen reduction method to testing for a number of reasons. The logistics of managing fecal coliform samples due to short hold times, cost of laboratory analysis, availability of labs, etc. So we did also look at alternative 2. So I plugged, we took the 2021, we took their theoretical MCRT. I calculated that from, the gallons that left the digester. We assumed full digesters because we don't have data. We don't have data to tell us what the levels of the digesters were to calculate actual volumes. But even at theoretical MCRTs for full digesters, you can see that a portion of the year, the MCRTs are below 40 days. And in all cases are below 60 days. And again, going back to what I was saying about alternative 2, we are limited to temperatures of 15 degrees and above. So during certain parts of the year, this alternative doesn't apply at all. So really, long story short, alternative 1 typically makes sense for aerobic digestion users. So then the next thing that we need to do is take a look at vector attraction reduction for aerobic digestion. We have really 3 options. Option 1 is, if you work with anaerobic digestion at all, you're probably very familiar with, and that's a reduction of volatile solids by 38%. This is very unusual to actually be able to achieve this in aerobic digestion. Also, the treatment plant did not routinely track this data in and out of their digesters, so we weren't able to calculate this with any certainty. Option number 3 would be to digest your digester contents on a bench scale at 30 days. For 30 days at 20C, if the volatile solids reduction is less than 15%, you meet vector attraction reduction that way. This is essentially an indicator of stability, that the volatile solids have already been significantly reduced in the digester, and this additional digestion doesn't show significant additional digestion. We don't see a lot of folks use this. Certainly Silver Spring Township had not done this in the past, but by far option 4 is the most typical aerobic digestion vector attraction reduction method, using the Sauer test. And the Sauer test has to be lower than 1.5 milligrams of oxygen per hour per gram. I know that's a mouthful. All that to say, it is adjusted for total solids and for temperature. So we did go and do Sauer testing at the treatment plant. We did this at the end of April. The digester temperatures are fairly warm, so we would expect, in a warmer digester, more robust microbial activity. We would expect to be able to meet Sauer in warmer temperatures. But the sour was actually almost double the standard. The standard is 1.5. The adjusted sour for this trial was 2.5. So not being able to meet vector attraction reduction obviously limits your ability. I mean, you can meet class B and you can incorporate do field VAR, but it certainly limits your ability to have a successful class B land application program. So, you know, being at the treatment plant, we felt like they had a considerable amount of digester capacity. We do see a lot of treatment plants that are short on digester capacity, and they just don't have the capacity to get the stability to meet vector attraction reduction, but it seemed that Silver Spring, relative to their size, had a considerable amount of capacity. So we thought we should take a look at their actual capacities in more detail. They do have 3 aerobic digesters. They have about 710 gallons of capacity, and they only waste about 750 gallons per month. So that is over 28 days of MCRT, even if the digesters are not decanted. But they do decant their digesters somewhat. The actual MCRTs based on 2021 data was between 30 and 50 days. If you remember the graph we looked at before, that was the graphical representation of that. So, you know, I wanted to compare that to some digestion design criteria to see sort of where they fell compared to what we feel like would be design standards. And, you know, 59 is 50 is 15C and 68 is 20C. So, you know, we would be in this kind of range for hydraulic retention time. So that's solid retention time without decanting. We'd be looking at somewhere in this like 50 plus days. So sort of, you know, they're sort of borderline as far as the design criteria to meet the standards. But I wanted to go take a little bit of a deeper look, and we've done some other work for some other utilities where we looked at degree days as a treatment time as a function of degree days. And so degree days is the product of the temperature in degrees Celsius multiplied by the SRT in days. That's the residence time in the digester. And this number can be used to evaluate aerobic digestion below 20C. We have a bunch of data from a similar treatment plant where roughly 300 degree days have been producing passing sours. That's a WAS only aerobic digestion, similar upstream treatment processes. So I wanted to compare using some sort of selected temperatures. SSTA doesn't track their digester temperatures routinely. So I just sort of selected a bunch of temperatures to use as sort of a benchmark to see if we felt like they would routinely pass this sort of 300 degree day benchmark. And you can see this is 20 degrees C, and then down to 8 degrees is the bottom line. We just used the monthly average MCRTs against those temperatures, and I plotted them against this 300 degree day benchmark. And as you can see, I mean, only at the lowest temperatures do we ever dip below that 300 degree day mark. And the months that we do is in the summertime. They have probably the most wasting in the summertime as they're adjusting from the spring. Bringing their MLSS down in their reactors. So we would expect that essentially they would meet this 300 degree day test all year long. So we started talking to the operators about how they operate their digesters. You know, there's sort of a couple of ways you can operate an aerobic digester. The typical thing to do would be to just sort of fill your digester with your waste activated sludge, aerate for a period of time, decant, remove whatever clear water you can, and sort of continue to fill and aerate, and then dewater when you can no longer effectively decant your digester. All 3 digesters could be operated in parallel like that. Or you could operate them in series. And if you operate them in series, of course, you feed one digester, you decant it until it's full. We transfer to the next digester. We do the same thing. We transfer to the 3rd digester. And then ultimately always dewater from that third digester. And what that does is maximizes your digester capacity because you're decanting as much as possible. It eliminates short circuiting, that is feeding the same digester that you would be dewatering from, which could put fresh undigested material into your digester, which could obviously skew your results. And really the important thing is it maximizes your time under aeration. Like that's the main goal, right? We're trying to get as much time under aeration as possible to create the most stable product. Because there's never been a beneficial use program at SSTA, they weren't really operating their digesters in either of these ways. They were really operating them more as what I would see as like an aerated holding tanks. If they had capacity in one, they would pump to that one. If they had capacity in another one, they would pump to that one. They would dewater whichever ones were full, but not really with, you know, with a real treatment scheme in mind, really just sort of pumping to places where they had space to hold solids. So I asked the operators if they had, of course, the ability, did they have the right pipes and pumps to operate in series, and would they change their operations to do so? And other than not being able to decant the one digester, which they decided to just do with the submersible pump they had on hand, they said that they could operate in series the way that we asked. And I went back in the wintertime and ran sour again after they had been operating like this for a few months. And at a temperature well below that 15C that we talked about, just sort of where the regulation stops for pathogen reduction, and, you know, a considerably cooler temperature than we tested and failed at in the spring, they were easily able to meet sour at 1.2 milligrams of oxygen per hour per gram of total solids. And, you know, I thought this was very convincing that we saw this kind of change through a simple operational change. So, I mean, they are, of course, going to now pursue coverage under the PAGO 8. That's a Class B permit here in Pennsylvania. Of course, meeting the standards is not the only thing that will get you a successful biosolids land application program. So I want to make sure we made this plug. Silver Spring Township is also installing cake storage. You know, to have a successful and cost competitive land application program, you really need to be able to manage your solids in a way that sort of falls in line with cropping and weather. And if you cannot meet total solids of 20% from dewatering, you are not allowed to store on the farm. So that basically severely limits your ability to haul and land apply during significant portions of the year, being the winter when we have freezing, when there's crops on fields, and really anytime the weather interferes. And Silver Spring Township does not dewater to 20%. So they are installing storage on site to sort of make this a more attractive and more successful land application program. And they are not planning any solids treatment upgrades. Of course, we're not talking about all the things that we've all been talking about that could come in the future. This is their plan to manage their solids before any of those triggers come into play. But I just thought this was a great example of being able to take the things that you have and make a few strategic changes and really see results on the other end. I think that's all I have for you guys. Here's my contact information if you want to reach out, and I'll be around for questions at the end.
Thank you, Wade. Yeah, it was pretty interesting. And I think it speaks to one of the challenges that we have in the Mid-Atlantic region, where, smaller facilities, sometimes the operations of their existing systems are not optimized. And, queuing in on that can really, really save clients some money. So appreciate that. All right, we're going to move right along here to our third presentation. We have a pair of co-presenters here. We have Dr. Robert Rubin, who is an emeritus professor of biological and agricultural engineering at North Carolina State University, and Robert Christie, who's with RDP Technologies. So as a quick bio on both these guys, so we know what's going on. Dr. Rubin is an emeritus professor, as I mentioned, at NC State University. He's been involved in water and wastewater management for over 50 years. Throughout his career, he's focused on land-based and natural systems for treatment and management approaches that are reliable, resilient, and sustainable. He was a visiting scientist at US EPA, where he helped with development of management and design guidelines for decentralized wastewater systems and other natural systems. And Robert Christie, he graduated with a BA from St. Joseph's University. He's been with RDP Technologies for over 11 years and has worn a multitude of hats, from project management to being the national sales manager. Rob's Biosolids tutelage comes from his father forcing him to inspect pug mills since elementary school, and his sister's background and numerous senior mentors within the industry. So our presentation number 3 is going to be on the beneficial use of thermally treated and line stabilized biosolids in North Carolina. So I will turn it over to you guys, Rob and Dr. Rubin, and let you get rolling.
Basically, what the goal is, I'm going to basically introduce the project and the process equipment that was used for the project. And then the majority of the time will then be spent on the results of the soil amendment that was produced. So without further delay, RDP Technologies basically started out cutting its teeth in line stabilization. It started off with Class B process, and then as soon as the 503s kind of became to the forefront of the industry, RDP Technology developed a process where they use supplemental heat to subsequently reduce the amount of lime, as lime wasn't probably the most efficient source species. However, lime stabilization originally became popular because it was the most cost-effective class A. However, a uniform problem with all class A processes was one, no volume reduction, and that would become more important as the industry develops and needs change. But the other problem was, if in an example,
Rob, I'm sorry to interrupt you. It may just be me, but I'm losing your audio a little bit here. So I don't
I'm
know
sorry.
if you could maybe
Am I
scoot
cutting
the
in
mic
and
to your
out?
mouth.
Can you hear me now?
It's a little better.
Okay, I'm sorry.
No problem. Thanks.
Nope, no problem. So essentially, if you had a 15% cake, what would happen is you would have a wet product going in, and you would basically have a wet product going out that wasn't stackable or friable. So the process is typically dependent on dewatering. Now, the only way that you can counter that, because there is no evaporation really going on of water, is the addition of lime to the product. So with the 503s, typically you need just enough lime for a pH to get to 12. And that typically could be anywhere from a 10 to a 25% lime dosage. However, with Class A stabilization, what would continuously happen was the addition of more lime to bulk the product up. And then you would be looking anywhere from a 60 to over 100% lime addition. That would not only add obvious operating costs, but with that amount of lime, you would significantly reduce the amount of acreage you could apply to a farm. So you would be getting negative benefits, both agronomically and at the wastewater treatment plant. And when RDP started with Class A stabilizations, this required a lot of studies to be done. And we started working a lot with Dr. Bob Rubin, specifically in North Carolina. And we continue today with this slide. It's showing another process where we're developing a composting process where we're using natural heat. The Morehead City is a coastal community, small coastal community with acidic soil. So because they have acidic soil, they were interested in lime stabilization for the benefit of treating the local soils. And they're also interested in a biosolid dried product where they were getting the volume reduction. And then subsequently in 2015, RDP had purchased the intellectual property to the Fenton dryer. Fenton had basically cut their teeth industrially, whereas RDP has primarily been in the municipal industry. So there was quite a bit of synergy there with their mechanical process and our know-how, and it became it was a pretty good fit for both of us. So as I said, Morehead City is a coastal community, small coastal community, and in venturing out into a Class A product, they were looking for a soil amendment that would best help them distribute the end product in and around the community. And in evaluating those two different technologies, they saw some drawbacks. And what RDP came up with was basically a third option, where we kind of tried to merge the two inherent values of either process and hopefully come up with a better solution for the small community. If you look here, this is just a really quick flow sheet of a typical batch dryer, which was kind of the premier technology for small communities at that time. You have a wide spot in the line for your sludge. You basically have screw conveyors coming in and out, and then a dehydration chamber in the middle for evaporation. Now, what RDP did was basically meeting in the middle. We added lime to the system. Now with the dehydration chamber, we don't have to, again, we're not dependent on dewatering anymore. We can get to a moisture concentration that is desirable both for the plant and volume reduction, but also for the local farming community. What that also allowed us to do was to get away with the traditional negative effects of lime stabilization. And because we weren't dependent on dewatering anymore, we can now add just enough lime to get the pH up to 12 and not add any more for a bulking agent. So this would also significantly reduce chemical costs for traditional lime stabilization. Skipping that slide. Natural gas still is a tried and true method for heating sludge. And with the thermal fluid systems, basically the nice thing about them is they're pre-engineered, and they have little really maintenance with regards to other technologies, specifically with steam or dusting issues. That's just the typical flow sheet of a system on skids from Fenton drying systems. One of the really key features that RDP added to really significantly enhance this process was putting the system on load cells. That basically allowed us to do three things. One, that allowed us to dial in the moisture concentration. It also allowed us to, this is a graph looking at a traditional batch dryer of where the optimal drying rate is. And it allowed us to basically optimize that. And lastly, automation, where basically the system can run pulse feed and pulse discharge both lime and sludge automatically, whereas opposed to the previous technology that was not possible. This slide basically explains the same thing. Moving along. So if you can see here's an animation of it. So basically, instead of running in a batch mode, RDP could evaporate to a certain solids concentration and then add more sludge. We could probably do this 3 or 4 times before you're starting to come up against torquing issues. But this allowed this system to become a lot more efficient, where we can get more sludge in contact with hot oil, the hot oil disc. And again, with this process, because we're adding lime, we don't have to go to 90%. We're technically a pasteurization process. So what the load cells also allowed us to do was optimize the solids concentration. So historically, this is a graph looking at what dryers will come across as they're going down the sliding scale to 90%. Because we add lime, we can basically get anywhere from a 55 to 75% end product, with our sweet spot kind of becoming 55 to 65%. So that on it, and that about gives us a 3-fold volume reduction versus a 4-fold volume reduction. So a question is kind of why pasteurization? And for this facility in venturing off into Class A, what they liked was the flexibility of pasteurization. It also has a commercial name similar to composting. And as Dr. Bob will talk about, it did necessary for the nutrient uptake with the additional chemical. If I can, hopefully I can play the slide very quickly. And if I can't, I'll just leave more time. It was working earlier, sorry. All right, moving along. So basically, I can come back to that. But in this slide, I think the most important thing, and this is from Daniel Williams, the utility director, and basically what they were looking for when they were going to a Class A product was something that was sustainable for the community, and where they could we're not relying on third parties. And the thought process here was coming up with a unique end product that, one, they were getting the volume reduction, but two, it was a beneficial reuse product where they could hopefully distribute it in and around the community. And as I kick it off to Dr. Bob Rubin, I was going to leave with this slide where hopefully we can show the benefits of maybe adding a little bit of lime can be a positive influence. So with no further ado, Dr. Bob Rubin.
Thank you. And just go through the slides real quick, if you would, please. That's me, and I'm not going to belittle that. Yeah, I think our goal, I think everybody in the biosolids industry has the same goal, and that is to develop a comprehensive approach to wastewater treatment and solids management that will assure the recovery of nutrients, energy, and water in a sustainable manner. That is what I call the news paradigm, or the news program. And we certainly have achieved that in Morehead City and some of the other applications here in North Carolina. Next, please. Residuals, you all know this, so I'm not going to belittle this, but residuals are a significant management issue for municipalities, for wastewater treatment operations internationally. It's not unique to North Carolina or unique to the states. Next, please. And land application does have a lot of benefits. We can do PFRP, Class A product, fewer site restrictions. We can do Class B product with more significant site restrictions. Here in North Carolina, our biggest restrictions are separation distance to water table. With Class A or PFRB product, we don't have to worry about that anymore. Next slide, please. So we're looking at biosolids both as a nutrient source and as a source of organic matter. Many of our soils in North Carolina are losing organic matter, and I firmly believe that one of the best ways to sequester atmospheric carbon dioxide is to put that carbon in soil and build soil organic matter levels. We have done some work looking at that with our turf crops, with our row crops, and with some of our forest crops. And our issues and what it is and how will it be applied, how will it be best used, what are the nutrient levels. All plants need nutrients, and there are limiting nutrient additions that can be applied to land here in North Carolina. Next slide, please. We are required to develop a nutrient management plan that really optimizes the potential uptake of nutrients in plant material. Nitrogen and phosphorus are the two nutrients of greatest concern here. Next, please. So if you look at the nutrient levels in the thermal process material and the thermal process material that we incorporated with compost, you can see that the thermal product with the compost had a little higher level of nitrogen, pH was a little lower, and the ag lime equivalence was a little bit, it took more product to equal a ton of agricultural lime. But because we weren't lime limited, we could apply more biosolid material as compared to just a lime only addition. And our nutrient management plans, we are required to look at carryover nitrogen and carryover phosphorus. In all of the samples we did, let me note that the regulated metal levels were all below the table 3 values in the 503 rule. Next, please. So my job working with RDP was to try to show some of the benefits of both thermal process material and the thermal process material that we commingled or co-blended with compost. And yard and leaf waste, some food waste, materials that occupy space in landfills can be composted very nicely. And by mixing these two materials, the thermally processed and lime added biosolid with the compost, we were able to get excellent crop yields and good high quality crop materials. Okay, and you can't see very well, but you can see some of our plot studies in the field. This, I don't know if you can see this. This is the compost blended. This is the thermal process, and this is our control area where we really didn't add anything. And this is just commercial nutrients and lime. Next, please. And again, our comprehensive nutrient management plan is to provide a balanced agricultural application that's consistent with crop need. Next, please. And by the way, the 590 standards apply. So we have to look at what we call the right rate, and that's the nitrogen need and the phosphorus needs of crops. Here in North Carolina, we have specific crop yields and crop equivalency factors based on soils in the specific counties. And you can download all of this from the Soil Science Department website at North Carolina State University if you're interested. Next, please. And the important thing there is those realistic crop yields and realistic yield expectations. We have managed our nutrient program based on actual crop yield data associated with the counties in North Carolina. And we think that these are realistic and based on about 30 years of crop yield and crop test data through our Department of Agriculture. Next, please. So again, this is typical for any land application program. What are the crops? What are reasonable expectations for yield? What do soil test results currently show? And what can we do to control losses from the site, both leaching potential and erosion control? And
Might have locked up there.
Maybe we lost you, Dr. Bob. Frozen in time. Well, we'll give him, I guess, a minute to see if he reconnects.
Sure.
I don't know, Rob, if you wanna roll through some of his items.
Well, if unfortunately Dr. Rubin can't come back, what I'll do is I can roll through the slides real quick and we can just conclude. Okay.
I think he was just getting to answering my questions.
I know.
Well, considering where we're at,
Okay.
maybe
Not a
I would pose addressing some of the Q&A items, and if Dr. Bob is able to rejoin us and people can stick on, maybe we could have him finish his slides up here at the end. So, thank you, Rob. So, All right, thanks again to our three presenters. I think we had some good discussion here. We've got a question or two that's floating out here on the Q&A. So if anyone else has any thoughts, comments, direction for future presentations, feel free to put those in the Q&A, but I'm going to pose a couple of these questions and then we'll let everyone go. Valentino, I think this was for you. I know that you spoke some on the permitting aspect of your system, but maybe you could expound upon that and specifically touch on how long it's taken for you guys to obtain permits for some of your various sites and how that climate might be changing as there's more installations and more is known on the PFAS destruction end of it.
Absolutely, that's a great point, great question. I'd be happy to expand onto that. So I probably haven't mentioned, but we were, and I believe we're still the only producer at full scale of biochar from biosolids, feedstock only in the whole United States. So being first, of course, has many advantages, but also many disadvantages, especially in the industry that we serve. So permitting for the first deployment installation back in 2016, where we first started, was pretty difficult, I have to be honest, right? So it took us about 1.5 years ish to work with EPA as far as understanding, for them what pyrolysis is versus incineration or other thermal processes that have been done before that were, of course, more well known compared to pyrolysis. And so that, again, took between 1 and 1.5 years. The good thing is we did it back in 2015, 2016. There's no need to go through all of that again, because, again, we received the approval from the EPA federally that applies to all of our units, right? Dealing with the Bay Air Quality Management District here in San Francisco was even worse, right? So of course we didn't know. I came fresh out of the boat, 10 years ago and say, yeah, let's start this journey in the United States. And of course we choose the most difficult place to begin, our journey in San Francisco. We didn't know. It was a good thing because, it took us close to 3 years, very challenging for a startup, for any business, to wait for 3 years, to have, such a big milestone to happen and unlock, avenues for the future. But we did it, right? So the problem, let's call it problem back then, dealing with the Bay Air Quality Management District and anybody else, was simply the fact that has never been done before. So nobody really knew what to expect, what emission profiles to expect, even the category of, how to best categorize pyrolysis, right? So it was a bunch of educational work that we did after 3 years of permitting and successfully, permitted with no, complaints, no claims, and nothing of that sort from, permitting standpoint. Now I give you another 2 examples. In Pennsylvania, we have a facility in construction within Lancaster County, Ephrata Borough Authority. Permitting in Pennsylvania, I think, took us about 1 to 2 months for the full permit, right? So I don't think it's even, considerable as a problem. And in California, we have other 3 facilities that are being built. Permitting took about 3 to 4 months. So my point is the challenge was very much being the first, still the only one, but at least now we have a lot of data, a lot of testing, source tests that we can, present together with the permitting application. And we have references and case studies that, of course, other agencies can utilize and look for more information and understanding. So we're very well positioned now to have a pretty quick and efficient permitting process. And again, we can receive permit from east to west of the US. Since we already made it in San Francisco, like you make it in New York, you can make it anywhere else. Same thing here with what we do in San Francisco now, very much open up to any other jurisdiction to install and get a permit or permits for our type of equipment.
Okay, good, thank you. Dr. Bob, I see you're back with us. We had just moved on to addressing some of these Q&As. We've got a couple more that are posed for Valentino here, which I would say we're going to run by him. And then if you and Rob want to hop back on and finish your bit, we will give you an opportunity to do that. Does that sound good?
Yeah. Okay, can everyone see slides.
Rob, I can't hear you if you're talking. Okay. Valentino, another one here for you, although we got Bob's slides up, would be about the percent of the biochar that's being sold.
Mhm.
And what the revenue, what revenue utilities are generating from the sale of that.
All right, so we are selling everything we produce at the moment, which is always a great thing to say. Sorry, I think my connection just dropped a second. Just want to see if I am back. You guys hear me? All right, sorry.
Yeah.
All right, sorry, I just went away for a few seconds for the connection problems here. But what I was saying that we're selling everything we produce mainly within soil amendment application. We have a great product and brand called Den Sustainable Soil that is selling pretty high volumes within boutique soil stores. Anthropology is one of the big names that buy our products, our soil mix, for example. And then we move product within pigmentation and the concrete, right? So the avenues that we believe are going to be the most valuable and effective, especially to move larger volumes, it very much doesn't matter the location, also the installation, are going to be within the concrete additive and soil beneficial use opportunities, right? So what utilities have been doing first is to delegate and to entertain with Bioforce as far as dealing and managing the carbon products. So we are actually we have contracts with all of the utilities that we serve, but again, to manage their product for the next 20 years, right? Expected revenue sharing, so the percent of the profits that utilities can expect, it is nothing let's say considerable at the moment. Like they are not going to be can become rich. The point is they are stopped paying to get rid of waste, right? And that is true for 20 years. That's the icing on the cake, right? What they can expect as far as revenue back is between $15 to $30 per ton of our carbon at the moment. All right, so this is the expectation they can consider. That's part of our value proposition and the budgetary proposals as well, knowing that this market is, the destiny of this market is just going to be rapidly growing. The movement for carbon credits, for carbon sequestration, that have been priced, pretty highly from Europe to North America. And we believe the next 10, 20 years, the price of carbon will just be increasing pretty dramatically. And so the more we also develop avenues and opportunities to offtake and beneficially reuse our carbon, of course, pricing and revenues will be dramatically increasing. So even utilities will be expecting more and more and more as we develop the market in the next few years.
Okay, great. Another one for you here. How much outside air is added to the bio dryer to enable the autothermic drying or heating? And is that airflow constant? Also, what do you have to do to mitigate odors?
All right, so I missed the first part of the question. Can you repeat that, Logan? Sorry, my connection was a little bit spotty.
Sure. How much air is added to the bio dryer to enable the heating? So
yeah, it's a complete aerobic process. So absolutely, it is not anaerobic. We do not produce any H2S as far as constituents for discharge air. The airflow modules and varies depending on the processing conditions, right? The peak flow of air, I believe, is 2,700 SCFM per each dryer, and that is through the thermal drying phase. So when we push air at max speed continuously to finish up that drying batch. During the biocycles, when bacteria are, sort of doing their job, utilizing their heat to dry biosolids, the airflow is not constant and continuous. It goes off and on. Of course, I cannot disclose, how often, goes on and off because it's part of our trade secrets, but it's going to be dependent on what the software decides based on the processing condition and the what it reads from the process between temperature, moisture, air pressure, and so on to decide when to give air and not when to give air. Last part of the question, I think it was how do we mitigate odors? So air emissions from the biodryer are going to be mainly with VOC and ammonia, pretty standard in the industry for any thermal dryer, especially with aerobic conditions. We include abatement devices as part of our scope as well when we supply equipment. Normally, we recommend to combine a sulfuric acid scrubber with the biofilter to achieve most of the benefits as far as odor mitigation, being able to comply with the most stringent air permitting, especially here in San Francisco. But of course, that will be on a case-to-case basis because sometimes customers, utilities already have a scrubber that we can connect to with existing capacity. Sometimes they have a biofilter that we can connect to. So that will be subject to developments on a case-to-case basis, also understanding their sludge first and permitting conditions, right? But we have plenty of solutions available that again are commercially available, nothing that we invented because again, it's VOC and ammonia, very standard to be treated and removed in line with permitting conditions.
Okay, thanks, Valentino.
Thank you.
Rob, if you and Dr. Rubin want to finish your presentation, we'll give you guys a couple minutes here. I can't hear you, Dr. Rubin. Still no luck from you. Rob, I'm not sure if I can hear you either.
Can you hear me at all?
I got you. Okay.
Okay.
It looks like your mic is on, Dr. Rubin, but we're not getting any audio from you.
I think you might froze again.
Scroll back up.
Oh, there you are.
Did you hear me? Okay,
Yes.
yeah, just stop at any one of these.
Okay.
What I've done here, and I think these issues of crop yield and soil organic carbon are really important. We applied the materials on fescue crops, on row crops, on turf, and this is just one example of our agronomy. So site number one was the thermally processed material in compost. Site number two that you see over here was the thermally treated material only. Site number three is commercial fertilizer, and site number four is the levels in the crop, and you can see that the highest levels of nutrient were where we had the biosolid materials applied at agronomic rates. What's also very important is the soil organic matter levels. The soil organic matter levels started out at 0.8%. With the application of the biosolid materials, we increased soil organic materials on our fields pretty significantly, and also on our control sites. And soil organic matter is probably the best way we have to sequester atmospheric carbon. And we saw that on all of the test plots that we did for all of the crops. And that's really that's really all I wanted to say as benefits associated with this process. And I know we're almost out of time, and I apologize sincerely for my computer issue.
Not a problem, Dr.
I
Bauer.
don't think it's any skin off our back, Dr. Rubin. Everybody's got those things that happen. I appreciate you hopping back on and talking through. Sorry to cut you off there, Rob.
Yeah, I just wonder if Dr. Rubin had any other slides he'd like to walk through.
Did everybody hear my explanation of the fescue crop? Okay. We also look at sorghum. We looked at turf crops, and
Well, you might be in and out a little bit there, Dr.
Okay.
Rubin. So I know we have a couple Q&As here that are still on the list. And I'll pose a couple of those, and we're running up on the end of our 90-minute block here. So Wade, I had one for you that came in,
Okay.
which was, what will Silver Springs Township expect to pay for a beneficial use program?
Yeah, that's a good question. I realized I glossed over that earlier. We've been seeing full service beneficial use programs in our region. So that would be operated by, totally by a third party, like a Denali Synagro kind of group at like $45 to $55 per wet ton. So already less than what Silver Spring Township is currently paying for landfill, and certainly less than they would be paying if their price goes up. If they were able to manage that program somewhat on their own, what we call self-managed program, which is where they would sort of bid the transportation and work directly with the farmers, you could see additional price decrease from there.
Okay, great. I know it hasn't been too long since you completed that that analysis for them, Wade. How has continued operation and compliance with those operational changes been?
We have not gone back to them since then, but I haven't heard that things have changed. It's been a mild winter, so I expect that they've had pretty good luck with their digester. If we had a really hard winter, they may see some challenges during the really cold part of the year, but no significant changes since they made the operations move. They are seeing less solids come out the back door, of course, which has to do with the additional BS destruction, but they also put on some bioaugmentation process in their collection system, so that may have to do with that as well.
Okay, thanks.
Yeah.
Dr. Rubin, I pose one to you here. I know a lot of your research and discussion here was focused on North Carolina specific application, but could you speak a little bit to how, maybe the Mid-Atlantic region or even nationally, you would think that your studies apply?
Thank you. That question. And acids in soils in the Northeast, you have acid soils in the western part of the country. So I think as you start looking at beneficial use, it's not just beneficial use as associated with crop yield. I think beneficial uses of biosolids should also address changes in soil organic matter levels. As a result of utilization of chemical fertilizers, we have seen all across the country reductions in soil organic matter levels. Utilization of biosolids and what I call biosolid derived products will help improve soil organic matter levels, nutrient status in soils. It doesn't make any difference where you are in the country. We see, and we have researchers at universities all across the country looking at benefits associated with biosolid materials. So it's not just here in North Carolina, but these are sustainable sources of nutrients, sustainable sources in many cases of liming materials, and not just nitrogen and phosphorus. But if you look at biosolids quality, there's everything in biosolids that we need to grow crops, everything. Did I answer your question?
Yeah, you did. I think, you know, we're kind of all in agreement with you there. So it's good to see that your research has supported that.
Well, and it's not just my research, it's researchers all across the country, I think, have documented this. And yes, I'm aware of some of the chemicals of emerging concern. And many of you are not old enough to remember Al Rubin, but Al Rubin was the father of the 503 rule. And his saying was 503 is enough for me. Pat, have encountered in the last, I don't know, 10 years or so with all of these emerging chemicals really is a challenge to the industry. And I think there are many groups of people that are looking at trying to address some of these challenges in biosolid products.
Yeah, thank you.
Yeah, and that was an opinion only. Yes.
Valentino, one more for you that I missed here, but the question was posed: how does your system handle changing influent characteristics such as dosing bacteria?
So it is pretty able to modulate performances and adjust the processing conditions based on the material that is being processed. With that said, what we care the most, what the system cares the most, is consistency within the type of sludge or solids that need to be processed. I'm referring to primary, secondary, was only, digested or whatever that is need to be fed to the system, and the solids content after dewatering. So the system doesn't really care necessarily whatever happens before dewatering, so long as dewatering can be as consistent as possible, meaning that we do not, receive solids one day with 18% and the other day with, 30%. That's a big, gap, a big variation for the system to handle. And although if that should happen, is not anything dramatic for the system, again, to adjust itself based on the feeding input. It is key to process, that feedstock as consistently and as constant as possible. We have clients, for example, that wish to process, yard waste, food waste, and sludge, sometimes all together. I always recommend, and professionally speaking, suggest to, deal with sludge and potentially food waste within a single train of equipment, maybe through co-digestion. That is absolutely not a problem. Actually, we do that. We have references that speak on that. If you want to process yard waste, for example, we recommend to having a separate train of equipment because the characterization and composition of yard waste versus sludge is very different, dramatically different, I have to say. And from a permitting standpoint, from a technology and processing standpoint, and from a product output standpoint, it's best to keep those separate to have consistency, uniformity, and the processing, of course, will be reacting to those pretty quickly and efficiently, again, so long as we don't have dramatic swings, on a daily basis with different feedstocks, composition, and solids overall. So it is not a problem overall, so long as we can, manage that with, in a pretty efficient way. Let's put it that way.
Okay, great. Thanks for clarifying. Well, I think that we're just about out of time here, and we're out of questions that have been posed. So just want to thank everybody for attending this presentation, and thank all our presenters here for working through a little bit of adversity that we had with technology. And I think we still all got a lot out of this. So it was beneficial. Our next webinar in the series is going to be on May 2nd, which is a Tuesday, and topics on digestion. So I'm sure that Mary's going to be blasting some emails out here for everybody on that topic, and some stuff's going to be posted on the website. So with that said, I think we've wrapped it all up. I appreciate everyone. Taking some time here today with us, and for listening in. So have a good rest of your afternoon.
Thank you. Thank you, everybody.
Here, bye.
Bye.